I want to start our introduction to vectors by playing a video of a girl swimming across a river called the Kern River in Colorado. It's a river that has a very swift current. I want you to observe what happens to the girl as she swims across the river.
All
There
right.
she goes swimming across the river.
She's going very fast. I can barely keep up with her.
Notice particularly what's happening here. Notice the direction she's swimming and the direction she's going and the current.
She's got it.
Looks like she just barely has a chance to catch something here. She gets on the rock. She makes it across the river. Yay. She is safe. This is actually a very dangerous river to swim across, so it's probably pretty chancy that she did what she did. So here she's going to celebrate. Okay, so we're going to go back to the notes now.
All right.
Now what you noticed is that the swimmer started out swimming this direction. So this was her initial direction. And she had some kind of velocity going on here. Okay, she was swimming at some sort of speed. And then we had the current of the river that was going this way. So this is the current of the river, and it pushed her so that when she started out swimming this way, she ended up at the end, she ended up swimming this direction. So she really got pushed from one side to the other by the current. All right, so these are examples of vectors. For the next example, in class I used 3 people to do this, but I don't have 3 people here. So this was where one person was located. Another person was hanging onto one of this person's arms, and a third person was hanging onto the other of the blue person's arms, okay? And one student pulled this way and another student pulled this way, and we want to know what happened to the student in the middle. So I'm going to illustrate this by pulling on the strings. So if I pull on both strings, notice what happens to the blue student. Okay, which direction does he go? Okay, so I'm going to close this, and that's this other illustration. So if we had the students, if we represent the students with some vectors, we would have one student. So here was our student here, and there's one arm stuck out this direction, and one student's pulling him this way. Another arm stick out this direction, and another student's pulling him this way. And what direction does the student end up going? Right up the middle. Okay, so that's another illustration of a vector. So let's just define what a vector is, and then we'll do a couple of problems related to these 2 examples. A vector is a mathematical quantity that has both magnitude and direction. Magnitude is just another word for size. The magnitude or the size is represented by the length of the vector. The direction is represented by the angle or the slant or the slope of the vector, which direction it's pointing. Okay, so you notice that every vector I drew has an arrow that tells which direction it's going, and it's drawn at a certain angle to tell the specific direction it's going. Vectors can be used to represent different types of quantities. In the swimmer problem, we use the vector to represent velocity. How fast the swimmer was swimming, how fast the current was going. We could have also used the vector to represent how far she went. So distance, or what we would actually call displacement. Displacement is the technical word. Distance is just is a quantity that doesn't have direction to it. Just like velocity is another name for speed, but speed doesn't have direction associated with. Speed is just a number. Velocity also includes direction. Distance is just a number. Displacement is change in position, and it involves a direction. The third thing that vectors often are used to represent is force, which is what we illustrated when somebody pulled on this person with a force going this direction and another force going this direction, the total force exerted on the student actually pulled him this direction. Okay, 3 other fun facts about vectors and a little bit about vector notation. Okay, so vectors are added tip to tail, not tail to tail. So if I draw a vector, this is called the tail of the vector, and this is called the tip of the vector. So we can think of the tail as kind of the starting point of the vector, and the tip is where it ends when we go in this direction. When we want to add 2 vectors together, I would have to draw a second vector connected to the tip of the first vector and going this direction. So we could add the vectors tip to tail. These 2 vectors are in a position to add. When we add them, then the result goes from the beginning or the tail of the first vector to the tip of the second vector. So this is the sum, or we call this the resultant vector. So if we call this, so we're adding these 2. So I'm going to put these together. We're adding these 2, and this is the red one is the sum. And we call this the resultant vector. Now, we don't add vectors tail to tail. Okay, so if we have 2 vectors that are tails, their tails are together, not in the position to add. Okay, so these are not in the position to add yet. We'll have to do some shifting, and I'll explain more how that's done with our example problems. Well, actually, I can explain that in just a minute, because with our next thing, vectors are, actually it's our third point. Vectors that are being added must represent the same type of quantity using the same unit. So for example, if this vector in my problem up here with the swimmer represents velocity, then this vector also has to represent velocity, and this vector also has to represent velocity if I want to combine them. If I want to add them together, they all have to have the same units. And if this one's in miles per hour, this one has to be in miles per hour, not meters per second. Okay? If these vectors are all representing force, they all have to have the same units of force. If our vectors represent distance, they all have to have the same units of distance. Now the third, so that's number 1, number 2. Number 3, a vector can be moved parallel to itself and still be the same vector. So for example, this vector here, this black vector, grab a hold of it, I can move it anywhere on this paper and it's still the same vector because it's still the same length and it's still pointing the same direction. So I can move it anywhere I want, and the fact that I can move it, so I can also move this vector anywhere. So if this vector was, these vectors were originally tail to tail and I couldn't add them, all I would have to do is shift this vector up to here, and now it's tip to tail and I can add them. Okay, so that's how we put vectors in a position to add. So in this vector, I can move one of the vectors over here in order to add it. Now the last thing I'm going to talk about in this video is the notation. A vector is denoted by either putting a little arrow above it. So let me make this kind of bigger so you can see it. Okay, a little that's called a vector hat. Or if sometimes when it's in a book, we see it in bold print because it's a little harder to put the vector hat in some sort of print. This is the resultant vector, the sum of 2 or more vectors. So when I'm indicating a vector, I put this little symbol over it to represent that I'm talking about a vector, not just a number.